Layered architecture is a software design pattern that organizes a system into layers, where each layer has a specific responsibility. This approach separates concerns, making the system easier to manage, develop, and maintain. Each layer only interacts with the layers directly above or below it, ensuring a clear and logical structure. Key concepts of layered architecture: separation of concerns. Layered architecture is built on the principle of separation of concerns. Each layer focuses on a specific aspect of the application, ensuring that changes in one layer don't directly affect others. This makes the system more modular and scalable. Layers in the architecture. Typically, a layered architecture consists of four main layers. Presentation layer, the topmost layer that interacts directly with users. It's responsible for UI/UX and handling user input. Examples include web pages, mobile app interfaces, or command line interfaces. Application layer, service layer. This layer contains the business logic of the application. It processes data received from the presentation layer, applies business rules, and makes decisions based on those rules. For example, in an e-commerce application, this layer would handle the logic for placing orders, calculating totals, and applying discounts. Business logic layer, domain layer. Sometimes combined with the application layer, this layer represents the core functionality and business rules of the system. It's where the actual processing and calculations happen. Data access layer, persistence layer. This layer is responsible for interacting with the database or any other storage mechanism. It handles CRUD, create, update, delete operations, and abstracts the data storage details from the rest of the application. Database layer. At the bottom of the stack, this layer is responsible for the actual storage of data. It's where the data is physically stored, often in a relational database like MySQL, PostgreSQL, or a NoSQL database like MongoDB. Advantages of layered architecture. Modularity. Because each layer is independent, changes to one part of the application don't necessarily affect the others. This modularity makes the application easier to develop and maintain. For instance, a change in the data storage method would only require modifications in the data access layer, leaving the other layers untouched. Ease of testing. Layers can be tested independently, allowing for more focused and effective testing. For example, you can test the business logic layer without worrying about the UI, ensuring that the core functionality works as expected. Reusability. Layers can be reused across different projects. For example, the same data access layer could be used for multiple applications that interact with the same database. Real-life example: e-commerce application. Consider an e-commerce platform. The presentation layer would be the website or mobile app where users browse products and place orders. The application layer would handle the business logic, such as applying discounts or calculating shipping costs. The data access layer would interact with the database to retrieve product information, customer details, and order history. Finally, the database layer would store all this data, such as product catalogs, user accounts, and orders. Associated concepts. Layer communication. In a layered architecture, layers communicate through interfaces. The presentation layer, for example, doesn't need to know how data is stored. It simply calls an interface in the application layer, which in turn interacts with the data access layer. This communication flow ensures that each layer remains decoupled from the others. Layered versus N-tier architecture. Though similar, layered architecture and N-tier architecture are not identical. Layered architecture focuses on the logical separation of concerns, while N-tier architecture refers to the physical deployment of these layers across different servers or systems. For example, in an N-tier system, the presentation layer might be on a web server, the application layer on an application server, and the data access layer on a database server. Dependency inversion principle. In layered architecture, the dependency inversion principle can be applied to ensure that higher layers, like the presentation layer, are not tightly coupled to lower layers, like the data access layer. This is often achieved through interfaces or abstractions, allowing the higher layers to remain flexible and adaptable. Use cases and examples. Banking systems. In a banking system, the presentation layer could be the ATM interface or mobile banking app. The application layer would manage transactions, account balances, and customer interactions. The data access layer would interface with the database to store and retrieve account information, transaction history, and customer details. Healthcare systems. In a healthcare management system, the presentation layer could be a patient portal or a doctor's interface. The application layer would handle scheduling, patient data processing, and medical record management. The data access layer would interact with the database storing patient records, appointment histories, and billing information. Challenges? Overhead. While the layered approach offers many benefits, it can introduce overhead in terms of both performance and complexity. Each layer adds additional processing, which can slow down the system. This overhead needs to be carefully managed, especially in performance-sensitive applications. Rigidity. Strict adherence to the layered architecture can sometimes lead to a rigid system where simple changes require modifications across multiple layers. This can make the system difficult to adapt to new requirements or technologies. Conclusion: layered architecture is a powerful design pattern that promotes modularity, reusability, and ease of maintenance. By separating the system into distinct layers, it allows for independent development, testing, and deployment, making complex systems more manageable. However, it requires careful planning and design to avoid the potential pitfalls of performance overhead and rigidity.